All right, so good afternoon. We're going to go ahead and start on chapter 5, describing distributions numerically. A little quote here that, he uses statistics like a drunken man uses a lamppost. He's using it for support, not illumination. And we're getting to a kind of a point of statistics here. What we're speaking to in this is that when we use statistics, we want to use them to give us some information about the world, not just try and further a point of view we already have. So really quickly, what we're going to do in this section is we're going to learn how to quantify some of the descriptions we have, the centers, the spread. How are we going to use our median and IQR, interquartile range? We're also going to be able to use this to create box plots by hand or by using the calculator, TI-83 or an 84. And we're also going to focus on the mean and standard deviation for symmetrical distributions. So first thing is we have our measures of center. First one is our median, which is simply the middle value. This is a value that would divide the histogram into two equal areas, so that our median, if it has 5 entries to the left of it, it'll have 5 entries to the right. This one where we found it by we put all of our numbers in order, increasing or decreasing. We find the value that's just the middle value. It has the same number of entries to its left and to its right. Mean, it's just the point where the histogram would balance. This is the mean, the average that you've probably been using in most classes up until now. Now we have our measures of spread. We have quartiles, range, and then we have the interquartile range. Now quartiles are pretty useful. Oh, and of course, we're going to have our standard deviation. Now our quartiles, we have Q1, which is a 25th percentile. So at Q1, 25% of the data has that value or less. The median, sometimes called Q2, this is the 50th percentile. It's the middle value. Half the data is going to be above it, half the data will be below it. We also have Q3, which will be the 75th percentile. So our quartiles are positions, and they tell us how much things are spread out. Now we have range. Range is the most simplistic of all of the measures of spread that we have. It's just the maximum minus the minimum. It's a bit like if I told you the range of temperatures. I'd look at last year. If the high for last year was 110 degrees and the low was -2, we had a range of 110 minus -2. We had a range of 112 degrees. But we didn't actually say what the temperature was, just how much it ranged over. Then we have the interquartile range. This actually gives us a bit more information. It's given by Q3 minus Q1. This marks off how much spread is there for the middle 50% of the data. Last, we have our standard deviation. This tells us how far each value is away from the mean. We can also name another way of saying it's the average distance from the mean of all the data. Now, whenever we have data that gives us a distribution that's not nearly symmetrical or not roughly symmetrical, we're going to use the 5-number summary to describe it. The 5-number summary is the minimum value, the Q1 of the data set, the median value of the data set, Q3 of the data set, and the maximum value in the data set. So let's take a look at set number 1 here. We have a 1, 3, 5, 20, and 22. So the minimum of this is pretty straightforward. It's a 1. Our maximum is 22. Now we look at our median. We want to find the value that's in the middle of the data. In this case, it's a 5. I have 2 entries to its left, 2 entries to its right. I also have my Q1. Now I can think of Q1 as looking at the data that is below the median. And if I look at that, it's just the numbers 1 and 3. Well, I don't have a number in the middle of 1 and 3. So instead, I add 1 and 3 together, divide it by 2, and I get Q1 is 2. Same thing for Q3. Look at my data set. We've already used 5, so I'm looking at the data to the right of 5. It's 20 and 22. In order to find Q3, I have to add those together and divide it by 2, and I get a 21. Next, we have our range. It's just the maximum minus the minimum, or in this case, I have a range of 21. But my IQR is telling me my middle 50% of data. That's just Q3 minus Q1. We get 19. So it tells me my middle half of my data has a range of 19. So let's try data set number 2. Minimum again is a 1. Maximum also is kind of a straightforward one. It's 40. Now I got to look at my median. So I look at my data, start working my way in towards the center. I have 6 points of data. So if I take it and divide it by 2, I get 3. which would be the number 5, the third point of data. But that's not in the middle. So instead what I have to do is I have to take that 5, add it to the 20 to get 25, and cut it in half. So I get 12.5. I have to find what would break that data in half, so I'd have the same number to the left as I do to the right. And that'll be the average of those two data points in the center. Having done that, now I look for Q1. That's my data to the left of the median. So it'd be 1, 3, and it would include 5. So now I want the center point of that, it's 3. Now I do the same thing for Q3. I go to what's to the right of my median, 20, 22, and 40. 22 is the middle data value, so my Q3 is 22. Range, 40 minus 1, 39. IQR, Q3 minus Q1, or 19. Let's go ahead and take a look at data set number 3. Why don't you take a look at that for a second. See if you can figure out the min and max and the median. Pause video if you have to. Okay, well, min and max, pretty straightforward, 1 and 50. And now take a look for that median. We have 8 points of data. So I divide that in half. That's 4. I want the 4th and the 5th point of data averaged together. I count those in. That'll be 20 and 22. Divide it in 2, and I get 21. Now I look at what's to the left of that 21. And that's 1, 3, 5, and 20. I need the middle point of data. I don't have a middle point. So I'm going to take 3 plus 5. I get 8. Divide it in half, and I get 4. We're going to have the same thing happen for Q3. Just like we had 4 points to the left, we're going to have 4 points to the right. But this time, I have 40 and 40. I add those together, divide by 2, add them together, I get 80. Divide in 2, I get 40. So my Q3 is 40. Range, 49. My IQR, 36. Let's go ahead and take a look at data set 4. Pause the video for a second. See if you can solve all 5, the 5-number summary, range, and IQR, following the same pattern we've been doing. Rewind the video if you need to see, again, how we did those previous ones. Okay, so I'm assuming you've paused the video if you needed to, you finished it up. All right, well, minimum's pretty straightforward, it's a 1. Maximum this time, that's a 140. Now if I look at all my data, I have 1, 3, 5, 20, 22, 40, 40, 50, and 140. I have 9 points of data. Take 9, divide in half, I get 4.5. Then I can just jump straight to the 5th point of data, and that's going to be my median. It's still going to be the 1 in the middle. So this time, I'm going to get 22. Now I look at what's to the left of 22 and find the middle. Left of 22 is 1, 3, 5, 20. Okay, I don't have a middle value, so I add them together. The 2 in the center, 3 plus 5, divide by 2, I get 4. Same thing for Q3, I'm sorry. Q3 this time, same thing, 22. To the right, I have 40, 40, 50, 140. And I take 40, add to 50, I get 90. Divide in half, I get 45. Range, this time 139 for my range. And my IQR, 45 minus 4 gives me an IQR 41. So what we're saying is that if we look at these, my range didn't really give me much information about my data. My IQR told me, even though I have a large range here, I'm actually clustering around, there's only about 40 points difference for everything in the middle 50% of data. Let's see how we can use this data. Okay, we use those 5, they're called the big 5, to construct a box plot. It's also called a box and whisker plot in order for our data set. Box plots are good when we have a lot of data to summarize, where you don't want to do things like a dot plot or a stem and leaf plot. Okay, there's just too much data to use stem and leaf plot, so we can use a box plot to summarize a large group of data. What we're going to lose are the individual data values, because we're only going to use these big 5. So think about that data set number 2. The first thing I'm going to mark on my box plot is my median. Then I'm going to mark my Q1 and Q3. And these are where I'm going to have my box. My median gets marked. Then I go down Q1 and draw that mark. Go up to Q3, draw that mark. And then I put a box around them. Then, for just what's a box plot, I would extend the whiskers to the maximum point of data, which was a 40, and a whisker coming down to the minimum point of data. Let's go ahead and see what a box plot for data set number 3 might look like. So go ahead, look at your data you had. Draw this scale in your own paper. Mark the median, Q1, and Q3. Let's see if your boxes align with my box. So pause the video, take a moment to do that. And if you're listening now, that tells me you've unpaused the video. Your box should go from a little bit less than 5, have a median marked just above 20, and Q3 at 40. Now I draw my whiskers up to the maximum data point in data set number 3 and down to the minimum data set, or the minimum data value in data set number 3. Now, we can also do these in the calculator. Okay? So let's go ahead and try this in the calculator. We'll go back to our data for just a moment. So we have our data set on the screen. I have my calculator. And what I've done is I've already set it up now. I'm on the main screen. So to hit Stat, Edit, I'm going to load my data set number 3 into L1. So I have 1, 3, 5. Oh, I'm sorry. I have a typo already. Let's try that again. 1's correct. And we have 3, 5, 20, 22, 40, 40, and 50. Go ahead, take a moment. If you have the calculator, type in your calculator also. If you have the emulator, load it in the emulator. We have our data inside of L1. Okay. Now I want our 5-number summary. So I hit second quit. I hit Stat, Calculate. I want one variable statistics. My data is in L1. I don't have a frequency list, so I leave it blank. So now I want to calculate it. I can scroll down now. It already gave me some data. I have my mean, my X bar. I have a sample mean of 22. Let's scroll down. It tells me I had 8 points of data, but my minimum was 1. My Q1 was 4. My median was 21. Q3 was 40, and max was 50, which is exactly what we'd already found using our own. So let's go back in, take a look again now. So we can use our calculator to do it. Now, the other thing we're going to have, and we'll talk about it, so we have a modified box plot. Now, modified box plot, we mark the outliers. Outliers are defined. They are any data points that are more than 1.5 times the IQR above Q3, or that are less than 1.5 times the IQR below Q1. What that means is in data set number 4, we had an IQR 41. So 1.5 times 41 is 61.5. I would add that to Q3 and find an upper boundary or an upper fence of 106.5. Any data point or any value above 106.5 we would consider an outlier. Similarly, I take Q1 and subtract 1.5 times the IQR. I have negative 57.5. So anything less than negative 57.5, we'd also call an outlier. These are our boundaries. Boundaries are not actually part of our box plot, though. Now, in our data set, we had 140. 140 is going to be an outlier. So we would have marked it on our modified box plot. Oh, and let's show what that would look like. So we're going to use something quick we can graph on. Okay. So we'll use this slide. Let's duplicate this. We'll use this slide to show our modified box plot. In this case, our number line isn't quite going to go far enough for us. So let's get rid of that. The first thing we need is we'd have our number line at the bottom. We have to put our scale on our number line. Or in this case, we know our bottom value is 0. The upper, as far up as we have to go, is 140. So go to 140. So we have a scale. Now we know the center point then is about 70. Normally this is how we want to do this. So let's put that 70 in there. This is our middle of our graph if we're keeping everything to scale. And we cut this in half again. Well, it looks like we were just there. Okay. Cut that in half again. We'd have 35. And if we work on our other side, 35, that'll be 105 on this side. Now, this is not the nicest way to have numbered all these. We'd want these numbers to end in tens or in zeros, but this will work. Now, our data set number 4, we had a median of 22. In fact, let's put this in our calculator so we can go back and forth. So stat, edit. So we had 1, 3, 5, 20, 22, 40, 40, 50, and 140. So you need to go ahead, pause the video, enter those in your calculator so you have something to work with. And if you've got me playing again, that must mean you finished putting that in your calculator. So you do stat, calculate, one variable statistics, L1, no frequency, we calculate. Then we scroll down, and here's all of our data. My median is at 22, so I need to mark my median. And we'll just use a line for this one. So if this is 35, we're going to say 22 is right about here. Okay. Now I actually need a box going up to Q3. If we look, Q3 is 45. So we draw a box going up to 45. We'll say it's 45. And we won't fill that in. We'll leave that empty on the inside. I was saying a box going down to Q1. Q1 was 4. So my box now goes from my median down to 4. That actually looks about right. That doesn't look too far off it. Maybe it should go a little bit further. Okay. Now let's look at my boundaries again. So my boundaries were 106.5 and negative 57. Well, nothing is going to go, I didn't have any data down to negative 57. So I can draw that whisker right now. I'm going to have a whisker going all the way down to 1 with no problem. Doesn't want to draw anything nice and straight for us. That's okay. We understand that's supposed to be a straight line. Now we have to look at our other side. Our boundary was 106.5. I cannot draw a whisker past the boundary. It's just not allowed to be done. So instead what I do is I would mark my paper with a temporary line as I'm drawing this. I would say, okay, I know I cannot draw anything past 106.5. And we'll say it's right there. But what I need to do is draw my whisker to the highest point of data I have that isn't past the line. So let's go back here. 50 is the highest point of data I have that isn't past my boundary. So I come back down. I need to extend this box, which currently ends at 45, to go to 50. That's not going to go very far. I'm going to take it and extend that to 50. Now, we cannot ignore our outlier. Remember, in our original data, we had an outlier at 140. We can't ignore that. We do have to graph the outlier. But it's past our boundary. So instead what we do is we use another symbol for it. Now, there's a lot of symbols you can use for it. Okay. We know it's going to be up here way at 140. So we're going to appear to 140. Now, this is what we commonly see. You can see a hashtag. Sometimes that's used to mark an outlier. Another very common symbol is an asterisk. Another very common symbol is just a small 0, or more like a little O, or a small circle. Any of those work for marking an outlier. The main reason we know they're outliers is this is a box and whisker plot. That's not a box or whisker. Once we're finished it though, we've plotted our data, Q1, Q3, min, max, everything's been marked. Outliers have been marked. We no longer need the boundary. I would erase it. This would be our data set, our modified box plot. And I want to say it's data set number 5. I'm sorry, data set number 4. That's what we'd be looking at. So just by seeing the 140, I know there's an outlier to the data. I can also look at this and tell me a couple of things. One, my data was roughly symmetrical, except that outlier skewed it far to the right. There's a lot of things I can tell just from looking at this. Box plots tell us a lot of information. In fact, I'm going to go back to one of the other box plots. Let's take a look at that. This box plot, I've got a median. Q1 and Q3 are roughly symmetrical, but the max is much farther away from the median than the minimum is. So this means my histogram is trailing off and taking a long time to get to the last point of data over here on the right. So my data is skewed right. For data set number 3, this time we saw it was pretty roughly symmetrical. We look here, I'm going from 20 to 50. So it takes about 30 points of data to get to the end. Well, 22 to 1, it's about 22. If I had a lot of data inside of this set, I might call this roughly symmetrical. Wasn't a lot of data when making this set, probably won't call this roughly symmetrical. It's a little longer on the right. Because of the size of the data, I'd still say this is going to be skewed right. So using that information, one thing is if we should remember, and the calculator will generate these for us. So let's try that. We have our data in the calculator. We know that because we already did this. In order to plot it, we have to do second y equals. So we go into our stat plot. Make sure if you have any plots turned on that you turn them off. And go back into it. Now, we just want to use our first plot, so let's turn that one on. We arrow down one time. We're choosing the type of plot that we want. Okay. This first one is a scatter plot. It's a line plot, histogram, and this is our modified box plot. If you can see, it's a little tough to see. There are 2 small dots. That indicates that this would indicate outliers on it. My next one would not give me indicators for outliers. So let's go back to our outliers. And as soon as we do that, it changes our information. It says, hey, where's your X list? We said it's L1. Frequency is 1. We'll leave that alone. Then it says, what do you want me to use for outliers? Small open square, a plus sign, or just a dot. We'll leave it as a small open square. Now that you've chosen this, so let's exit from this screen. Second, quit. Just like before, we want to zoom in. We want to zoom into our stats. So we scroll down, and there's our zoom stat, number 9. So we hit enter. And it looks like there's some other things also being drawn. Let's say that y equals, yeah, there's something in there. Okay, saying quit, and we just hit graph. And here's our box plot. And we saw kind of what we drew. In order to see what these points are, we can hit our arrows and move around, but it'll take forever to hit those points. So instead we hit trace. Our minimum data was a 1. Q1 was at 4. Median was 22. Q3 was 45. Our highest point of data that wasn't past a boundary was 50. We arrow again to the right, and it tells us our maximum was 140. And if we had other points on here, it would include those just by going further to the right. In fact, just to show it, let's quit out. Let's modify our data. Let's add another point of data. Let's go ahead and add a 122. This would also be an outlier. And we'll add another 140. Now that's going to change some of our information though. So let's go ahead and make sure we're still getting some outliers. So our second stat plot, we can just second quit. And we hit graph and it'll redraw it. This time it eliminated our outliers. So adding those points of data changed whether or not we had outliers. So let's go ahead and remove that second 140 and go back into the graph. And this time we see we still have outliers. But now when we hit trace, our minimum is still 1. Our Q1 is now 5. Our median is now 31 because we add some points of data. Q3 is 50. Our maximum point of data that isn't above a boundary is 50. So if you notice, Q3 is 50. Maximum point of data that isn't past a boundary is 50. I'm hitting these, it's still showing me at 50 twice. So now I go up, I have an outlier at 122, and I have an outlier at 140. So it marked both my outliers for us. I can use the calculator to graph it, and then copy an orange sheet of paper if I need to. Let's get back to the main screen. All right, so let's go ahead and get back to this and try something new. So let's say LeBron James, oh, by the way, he did graduate from St. Vincent St. Mary's High in Akron, Ohio in 2003. This year, his salary is going to be $36 million. Well, if you were moving to Ohio and you had to decide whether or not to enroll your kid in St. Mary's, would you want to use the mean salary or the median salary of graduates? And what you want to think about is, what does it mean when something is the mean versus when it's the median? Well, LeBron James is an outlier in salary. He's making $36 million. Fairly safe to say most people who graduated from St. Vincent's are not making $36 million. So if I look at the salary of people who graduated from there in 2003, he's going to make that data become skewed right. His data, that $36 million is going to go into the mean, is going to drag that mean far above what most other people even made potentially. Because the mean follows the tail. If you're skewed right, your mean is going to become larger than the median. If you're skewed left, your mean is going to be less than the median. So in this case, the median is going to tell me what did the person make who is right in the middle of all the people's salaries. I'd probably want to use median because using mean, that $36 million is kind of like putting your thumb on the scale. It's putting too much weight on the scale compared to what else is there. So when the shape is nearly symmetrical, and we're going to transition to our new topic here. When a shape of our distribution, shape of our data is nearly symmetrical and there's no outliers, that's when we use the mean to describe them. Because that uses all of the values to come up with the center. But if I have outliers, I'm going to use a median. And X bar, that's my sample mean. It's still just the total of all the data added together divided by how many points of data I had. Deviation is just another word for difference between that value and the mean. So if I said what was an individual deviation, I would take that individual data value and subtract from the mean and figure out what's the difference between them. Variance is the average of the squared deviations. So I'd take all the deviations, I would square them, take their average by summing them and dividing by how many I had, and come up with a variance. Just like this. And it's called S squared, and there's a reason called S squared. So it'd be the sum of each individual data point minus the mean, but square them. So all those values become positive. We divide by n minus 1 because we're dealing with a sample. This X bar is a sample mean. Since we're going to have a sample, we want to give ourselves a little bit more wiggle room on what the variance of the population might be. Because I didn't do everyone, just a sample. So we only divide by n minus 1. Standard deviation, on the other term, is what we're going to use to describe the spread. The standard deviation is take the square root of the variance. Now, that's what we just called S. This is actually a much more commonly used term, so our calculator is going to report S to us. It's not going to give us S squared. To get it, we would just take our S and square it. Our calculator will find this data for us. So let's talk about what a standard deviation might look like and how we're going to find it. So I've got a class. I've divided into 6 groups of 5 students each. What I have here, their quizzes. Their scores they got, maximum of 20 points. And we want to figure out some data about those. So if we take a look at these, I've got group 1, group 2, group 3, group 4, group 5, group 6. I'm going to put all these in my calculator. And I save some time by doing most of them already. But group 1 needs to go back in. So we're going to go ahead and load that in. Let's do this first. Let's clear out the data that's already there. Now load in that first group. Okay. If we notice our first group, our mean is 10. I average all those, I find 10. Well, it turns out the same is true for all my other groups. We did that on purpose. So if I look at all my data from all my groups, pause the video, take a moment. You can load yours in your calculator. Load group 1 is L1, 2 is L2, 3 is L3, so on and so forth. Okay, so you should have unpaused the video. So you've loaded all this in the calculator. All the means are 10. In fact, I can see this by looking at it, and that tens, if I take the average of these, this can be 10. I see the same thing here. I have these 3 tens. The average of those is going to be 10. I just have to average 8 and 12. Well, I can take the 2 from here, put it with the 8, and I have 10. And 10, the mean is 10. The mean of 10, 10, 10 is 10. I have 0 and 20. Their mean is 10. So the mean of 3 is also 10. I do the same kind of balancing trick for group 4. Mean of 10 is 10. 8 and 12, their mean is 10. 0 and 20, their mean is 10. All those groups have the same mean. It's 10. All those groups are the same size. They all have the same mean. It's going to be 10. So on and so forth for 5 and 6. Do the same trick. 2, 18. That's 20. Divide by 2, I get 10. The mean of 10 itself is 10. 0 plus 20 divided by 2 is 10. Group 5 is also 10. Now, group 6, you might want to load in the calculator to do it, but you're going to find out its mean is also 10. So I can't just use the center to describe the differences in these groups, because we can see there are some differences in these groups. So instead I have to use other information. I can't just use the center. Also, 3 of them have a range of 20. 20 minus 0 is 20. So just using a range also isn't going to be enough information, because I couldn't tell, if I just use the mean and the range, I couldn't tell groups 3, 4, or 5 apart. So instead, we use some other things. Now, standard deviation, we said, is the average difference from the mean. If we look at group 1, they're all 10. They have no difference from the mean. Their standard deviation is 0. Now we're going to calculate for standard deviation for group 2. The way we do that, is we're going to use our calculator. So I've got group 2 loaded in a calculator. So I'm going to quit from this screen and hit hit stat, calculate, and one variable. This time we did L2. So I hit second 2. There was no frequency list, so I tell calculate. When I do that, I look at my list, tells me my mean is 10. I come down here to S of X. This is a sample standard deviation of 1.4142. Well, that's a little bit bigger than 0, so it does have slightly more of a standard deviation than the first group. So it's a little bit more spread out, and we can see that 8 is a little more spread away from the mean than 10 is. So we can try for the different groups. So go ahead, take a moment, pause the video. Have all this data loaded in a calculator. Whoa, bring that back. And we're going to calculate each one by just changing this to L3. And get our standard deviation. This time we get 7.07. So take a moment, do that. Get used to where that is in the calculator. Right. Okay, so if you're back, must have finished it. We found our group 2 had a standard deviation of 1.41. Group 3, standard deviation of 7.07. Ranges were 4 and 20. Now group 4, 5, and 6, the same thing. Standard deviation is 7, standard deviation is 9, and then standard deviation is 5. All these groups had some different data points. Now, what I can do to make this a little bit simpler is we can also graph our data. If we do that, look at group 1. They all had a 10, so let's put the marker at 10. There'd be many of them there. Now, what I'm doing is I'm marking the different points of data. So I had 10s, 12, and 8. I had 10s, 20, and 0. 10, 12, 8, 20, 0. 10, 18, 20, 2, 0. And group 6, we just had quite a bit of different looking data. And we notice our standard deviation changed. In fact, the more my data got spread out, the larger my standard deviation became. 4 is more spread out than group 3. 4 had a larger standard deviation than group 3 did. 5 was even more spread out than group 4, because these 2 points of data that originally were close to the mean shifted further from the mean. As we noticed, we saw that group 5 had the largest standard deviation. As we spread our data more and more apart from the mean, our standard deviation kept increasing. Now, standard deviation is a pretty good measure when our distribution is roughly symmetric and there's no outliers. Group 6 was not symmetrical, so I wouldn't have wanted to use this for group 6. Group 6, I would have instead have probably calculated the IQR and used that instead. So I wouldn't want to use standard deviation for non-symmetrical data or data that had outliers. So let's remember this. The mean is non-resistant. If you put an outlier in there, the mean is going to be heavily affected. LeBron James is going to affect the average income of people graduating from high school with him. But the median is resistant because LeBron is only 1 point of data. When we find the median, we're looking for the middle point of data, not the average middle, but the middle defined by how many points of data did I have? Let me find the middle one. LeBron isn't going to move that middle very far. If he went in there at 36 million or he went in there at $1 billion, he's still above the mean. He won't have moved it again. The median is going to stay where it is. If instead I put someone in there who also made $30 million, yes, they're above the mean. They're probably going to be above their median, but it's only 1 point of data. In a high school class of hundreds of students, that's not going to move the median very far. Now, range. Obviously, range is going to be affected by outlier, but the IQR isn't. Since the IQR is only the middle 50% of data, the outliers have been cut off. I mean, by definition, the outliers have been trimmed off from the data. All we're left with is the middle 50%. Outliers can't be inside the middle 50%, otherwise they wouldn't be outliers. Q1 and Q3, they're just like the median. They're marking that 25th percentile and the 75th percentile, respectively. They're not going to be influenced much by an outlier. So, do you think the standard deviation is resistant or non-resistant? Take a moment and think about it. Flip back to your formula and look at how the standard deviation is calculated and think about this for a moment. Well, so remember, standard deviation was the square root of the sum of the differences from the mean. Well, the mean goes into the standard deviation. The mean is not resistant. So if the mean is not resistant and is used to calculate the standard deviation, then the standard deviation is not going to be resistant. So think about another one. What kind of distribution am I going to have where the median and the mean are the same or at least pretty close to the same? Well, the median we said is our middle point of data. Our mean is where it would balance our histogram. Well, if my data is roughly symmetrical, I don't have any real outliers in there, my mean's probably getting up in the middle. So is my median though. So when I have symmetrical data, no outliers, my mean and median are probably going to be the exact same. Very important. Don't forget, you must report the shape, center, and spread of any quantitative variables distribution. If it's skewed, you're going to give the 5-number summary. If it's nearly symmetric, roughly symmetric, you're going to report the mean and the standard deviation. If you have outliers, we want to investigate those. They give us something interesting to look for. Why are they outliers? But also make sure you report them. If you have them, you have to mention them. They're part of our SOX. Remember, shape, outliers, center, spread. Don't forget your SOX in the morning. So at this point, you should have read Chapter 5. You already better have read Chapter 4. Had some suggested homework problems. The answer key was provided. And of course, finish up the Chapter 5 web work. And look forward to seeing you in class.